Hello everyone. So in this video, we are going to see Inrush phenomena of transformer. And like after watching this video, one should be able to answer what is flux doubling effect, what is inrush current, and how to avoid this phenomena from transformer. Okay. So basically, in this video, we are going to see the like we're going to analyze the inrush phenomena from intuition point of view. Also, we will see some mathematical derivations, like how it comes, how the flux gets doubled. So all of these phenomena we are going to discuss. So let's start. So for example, you have a transformer with you. You have a transformer with you. Okay, and the transformer is at no load condition. That means the secondary side is open circuit. And you have a supply. Okay, and you have this switch. Let's say this supply is nothing but Vs of t is equals to Vm sine omega t. Okay, and you are closing the switch at t equals to 0. Then what will happen? Let's say the primary turns is N1 and secondary turn is N2. Okay, now the moment you close the switch, the voltage that you will get some induced voltage here in the primary. Okay, now tell me one thing. If I assume the winding resistance is 0, leakage reactance is 0, so basically the moment you close the switch, this Vs and E1 will be exactly same. Okay, so we can write uh, E1 is equals to N1 d phi by dt. Can I write it? Yes. And since I ignored the winding resistance and leakage reactances and all, we can write E1 is equals to Vm sine omega t is equals to N1 d phi by dt. Okay. Now rearrange the equation. Vm by N1 sine omega t dt is equals to d phi. Okay, let me change the this term dt to d of omega t. So divide by omega sine of omega t d of omega t equals to d phi. Okay. Now you perform the switching action at t equal to 0, right? Let's say perform the switching action at t equal to 0. At t equal to 0, the flux in the core was 0. So we'll integrate it to calculate the flux at any given instant equals to d phi. Let's say you close the switch at t equal to 0, so that there the time is 0, the omega t equal to 0, and at that time the flux was 0, and maybe we wanted to know the what will be the flux at any given time t1 or t. So for that I am considering the upper limit as omega t, and the flux, the upper flux, that will be at any given instant omega t. Okay, now do the calculations. Minus Vm by omega n1 cos omega t 0 to omega t equals to phi of t minus Vm by omega n1 cos omega t minus 1 is equals to phi of t Vm by n1 omega 1 minus cos omega t is equals to phi of t. Now I am giving this Vm by n omega 1 as a, let's say I'm calling this particular term as phi m. Okay, so I can write my phi of t is nothing but phi m 1 minus cos omega t. Now try to draw this flux waveform. I got the flux equation phi t is equals to phi m 1 minus cos omega t. Okay, so if you draw, let's say it is omega t, this is phi of t. At t equal to 0, this cos omega t is will be 1, so this quantity will be 1. At omega t is equals to pi by 2, this particular quantity will be 0. Cos pi will be 0, so it will be simply phi m. And cos omega, and when omega t is equals to pi, then cos omega will be minus 1. Then 1 minus or minus 1, it will be 2. So at pi, the flux value will be twice of the maximum flux, like 2 of phi m, this phi m. So the waveform, if you try to draw, it will be somewhat like this. Okay, so at pi it will be maximum, twice of the maximum flux. Now from here only the term comes flux doubling effect. See, the maximum flux is getting doubled, and this maximum flux, this double maximum flux, is basically responsible to bring the core of the magnetic material in deep saturation region. We'll explain all of these things later. Now, this was the explanation from mathematics point of view. Maybe we can also think like how this we can also solve this problem, this how the flux is getting doubled intuitively also. Let's say, for example, if I assume my transformer has a high magnetizing inductance, it has no core loss component and all, and the winding resistance, leakage reactance and all are neglected, then my transformer can simply be represented by a magnetizing inductance Lm. Okay, Lm, and at t equal to 0, I'll be closing the switch. Okay, Vs of t. At t equal to 0, I'll be closing the switch. Now, initially, the core flux means at phi equal to 0 minus, the core flux was 0. So as per constant flux linkage theorem, flux cannot change instantaneously. Like if phi at t equal to 0 minus, flux was 0, at then at t equal to 0 plus, flux must be 0. Okay, this is something that we call constant flux linkage theorem. It is basically came from the energy conservation principle, like you cannot change the energy instantaneously, and flux is also related with the energy only. So like you cannot change the core flux suddenly, so it actually try to make the continuity in the flux also, as like in continuity in inductor current, and continuity in capacitor voltage. Okay, now, let's say if I assume what there will be a like after performing the switch, there will be some transient phenomena and there will be some steady state phenomena. Like at a steady state, let's say at a steady state, the flux that we are going to get, maybe at a steady state, let's say my flux is pi steady state of t. Maybe I can call it as a, let's say, minus phi m cos omega t. Okay, this is my steady state flux at of the core. Now the thing is, the moment you close the switch, this entire system gives response. Like the overall flux phi of t will have two component: transient component and steady state component. Okay, now the moment you closing the switch, from this equation number 1, you can see the steady state component at t equal to 0 is demanding is minus phi m, correct? But according to constant flux linkage theorem says that my flux should be 0. But here flux is getting minus phi m. So there must be another transient flux, that is phi m plus phi m, that will nullify this minus phi m, and it will make the flux to 0. So phi of t, so transient response of, or the transient component of the flux should be phi m, and the steady state flux is minus phi m cos omega t. Now, in this equation number 2, if you put t equal to 0, then this quantity will vanish and it will simply be 0. So it is basically now actually, what do you say, it is following the principle of the energy conservation or constant flux linkage theorem. So you can write, and basically one more thing that also I need to mention, the transient part should decay, and here the transient part basically it should be like this way, like it should have some maximum value and it will decay depending on the time constant of the circuit. Okay, but here the time constant is Lm by some resistance. Now my Lm is so high, there is no resistance, so my R is 0, so my time constant is huge, time constant is infinity. So if you put time constant of infinity at this equation, you'll get the DC value only. There will be constant DC phi m. So that's why uh, can replace the transient component by simply phi m. So that's the explanation, that because of the high time constant, the maximum flux will be phi m. So now the thing is, um, it is pretty clear, like from the intuition point of view, like you can calculate the flux, how the flux will behave if you perform some switching actions and all. Okay, now come to what will be the effect of this flux doubling effect. As I explained some other videos also, like the magnetic core is not a linear, it is a non-linear element. It is a non-linear core of the transformer. Now, let's say I am only considering the non-linear BH curve. Let's say this is my non-linear BH curve. Okay, and I have doubling flux like this. So up to this point, my current will be sinusoids. Okay, like it will follow the flux waveform nature, but this like this particular extra quantity, to produce that much amount of extra quantity, my current will be huge peaky in nature, huge peaky in nature, huge peaky in nature. And this magnitude of current can be sometimes go to 4 to 6 times of the full load current. And this full load current can actually damage the windings of the transformer if if it flow through the winding for several cycles of the like for few cycles. If it follow through that transformer winding, it can damage the transformer winding also. Now, like how can we avoid this phenomena? Now the thing is, how can we avoid it? Now let's say I have assumed my phi s of steady state flux is minus phi m cos omega t, right? So if we try to draw minus phi m cos omega t, so it will be something like that. It is my phi steady state flux. And if I try to draw the, if you see here, it is my pi by 2, pi, 3 pi by 2, 2 pi. Now, if you perform your switching action at omega t equal to pi by 2, at omega t is equal to pi by 2, instead of switching at t equal to 0, if you perform switching at omega t equal to pi by 2, at that condition, your steady state flux is 0. So it is basically satisfying the constant flux linkage theorem smoothly. So here you can do this soft switching actually. Now you can perform the switch and there will be no such transient or doubling effect. All those doubling effect was coming because of this constant DC flux. Okay, so it's anyhow we have to avoid this, so we can perform switch at omega equal to pi by 2, and this will not cause this doubling effect and induced currents and all. Okay, I hope it is clear. Now you got it, like what is the doubling effect, what is induced current, and how to avoid it. Yeah, thanks for watching. If you have any query, you can write me in that chat box. Thank you.